So some people have a question on how to set up stoichiometry for a problem like this for the gas laws. And so I'm going to do a quick video on how to set this up, and then maybe from there you'll be able to work out other problems. So this is number 5 on the gas stoichiometry lab for stomach stoichiometry. Lab 7A. So you always start with balancing the equation. So I'm going to rewrite this equation. C8H18 in liquid form plus oxygen. I'm leaving gaps so that I can fill in the coefficients for balancing the equation. And remember, don't change any of the smaller numbers when you're balancing. Those are permanent. Is going to yield carbon dioxide in gas form plus water in gas form. Okay, so if you drive 108 miles from East Lake to Disneyland in a car that gets you 22.4 miles per gallon, how many liters of CO2 are produced if it's 32 degrees and the pressure is 759 millimeters of mercury? So first, I would identify what each of these things are. So you drive 108 miles. This is a distance. So I write distance, 108 miles, and underline or circle. Then I go to my next number, 22.4 miles per gallon. So they went 108 miles, but they get 22.4 miles per gallon. So these two are associated, and I'm going to have to figure out a little bit of math there. And then how many liters, so how many liters, which is volume, of CO2, so I'm going to circle that I need, CO2, are produced if 32 degrees Celsius, which is temperature, so I put a T for temperature, and that needs to be changed to Kelvin. Remember, you don't want to use degrees Celsius when you're doing gas laws. And then as under a pressure of 759 millimeters of mercury. So this is going to be P for pressure. So I write down the formula I know I'm going to be using, PV equals, and I look, PTV, so PV, I have no moles or anything to consider, except for when I get down here, it's saying that 1 gallon of gas weighs 6.216 pounds, which is equal to so many grams. There is my N. So I am going to use PV equals nRT. So choosing the numbers that go in these places, you can't just put them in and then do the math. You need to do all your conversions first. And it looks like one of these is going to be a conversion. The 1 gallon of gas weighs 6.216 pounds, and a pound is 453.6 grams. Those grams are going to have to go to moles, because remember, N is in moles. So I need to start with that one. So I'm going to start with the miles per gallon. So they're going to go 108 miles, but they only get 22.4 miles per gallon. I figure out that they use 4.8 gallons of gas, and 1 gallon of gas weighs 6.216 pounds. This is 4.8 gallons, so I'm going to times that by the 6.216 pounds. So I can convert this to pounds. And then from pounds, I need to go to grams. And 1 pound is equal to 453.6 grams. So once I get my value at the end, so this is my pounds right now, I'm going to have to turn that to grams. But what I'll do is I will, if 1 pound is 453, this is whatever pounds I get out of this, I'm going to take that and multiply that by 453.6 grams. So I finally get grams in the end. This is what I need, and I need to convert that to moles. So I'm going to go ahead and plug in, well, I don't want to do all the math for you, so I just set this one up. So when you get to grams, take that to moles. And you can't do moles without knowing the balanced equation. So to balance this equation, you're going to count the carbons. So here's the long way to do it. And sometimes you just might have to do that if you can't figure it out by just going, oh, 8 carbons times 8, and then you keep working back and forth, back and forth. If that's too hard, go ahead and write down what you have on the reactant side and what you have on the product side. So carbon, I have 8. I have 18 hydrogens and only 2 oxygens. Over here I have 1 carbon, 3 oxygens, so I'm going to put that down here actually, and hydrogen, I have 2. So I need 18 hydrogens, so I would need to multiply that by 9, but let's start with carbon. I just know from experience that if you start with this leading atom, it's a lot faster and works better to balance the equations. So I need 8 here, so I'm going to times it by 8. That means I'm timesing this by 8. So 8 carbons gives me 17 oxygens now. So I cross that out and I put 17 now. And then for hydrogens, I still am short on hydrogens, so I'm going to times that by 9 so that I can match up over here the 18. So that gives me 18 hydrogens. And now that changes my oxygen, so now I have 16 and 9. So 16 plus 9 is 25 oxygens. Usually we don't like to have an odd number of oxygens because oxygen always comes as diatomic. So an odd number is going to give me a fraction, and I don't want that. So I already know my equation still is not accurate, but at least it gives me a jump start to kind of look around and say, okay, what do I need to do next to get this to balance? So since I don't want an odd number of oxygens, I got to be kind of careful of that. So let's look at here. 18 and 18 and 8 is fine. So our next step would be to say what number would I need next to get this to work. So normally you would take the hydrocarbon and change that, because that oxygen problem here that I can see, that's odd number, that's not good. I need to make sure that I can change one of these other ones, and I always go for the hydrocarbon. And when you take this hydrocarbon, I would double it or triple it or 3 or 4 times, whatever it takes to get this to balance. So you're not going to balance from this side. You're going to start the balance from the hydrocarbon on this side when it doesn't work down here. So I'm going to double that. Let's just go for it. This is 16 now, so I'm going to go 16 because I doubled it. And then that gives me 36 because I doubled it. And then oxygen is not affected. I'm going to use that to balance all the oxygens on this side. But I do need to get the 16 here to match this 16. So I'm going to switch this to 16. So that gives me 16 carbons. And then that gives me 32 oxygens plus 9 more. So 32. Well, we changed here, so we're not going to have 9 anymore. So let's change that. So 9's not going to work. I need 36. I'm going to have to times that by 2 again. So this is going to be times 2 more would be 18. And then that gives me 36 hydrogen. So times by 2, I get 36. 16. And we don't worry about this because that's going to change. So here I get 16 times 2 is 32 oxygens plus 18 more. And that gives me 10, 3, 4, 5, 50 oxygens. And to get 50 oxygens here, I need to times it by 25 to get 50. So I'm going to put 25 in here. And it looks like everything's starting to balance out now. So I check my numbers. 16, 36, 50. 16, 36, 50. So it's a matter of coming back and forth. But if you can't get it to balance the first time around without changing the hydrocarbon, go ahead and go back and double the hydrocarbon. If it still doesn't work, go back and triple the hydrocarbon. So that's the balanced equation, and I'm going to put those numbers 2, 25, 16, and 18 in here. 2, 25, 16, and 18. So that's balanced. And now I'm ready to finish up with my moles here, so I can apply that. So I have pressure. It's in millimeters of mercury. That's fine. So I'm going to write down what I do have now. So I'm going to have my moles, which you're going to solve. You're going to go grams to moles. Remember grams from periodic table in 1 mole. And that's gasoline. So this is gasoline. And which one's gasoline? This one. So I'm going to need that down here. C8H18, C8H18. Okay, and then your, just go down to volume, we don't know. Questionable, but we want it in liters, so make sure you know what you need it in, because it says how many liters, not milliliters, liters. So I'm going to make sure that's correct. And then we have temperature, which is 32 degrees Celsius. You need to add 273 to get it in Kelvin. So that's 5, and I'll let you do that one. You can do your kelvins. I almost did the math for you. You can do the math. P is pressure, and 759 millimeters of mercury is fine. But then you're going to have to go to your R value chart, and you're going to have to choose the one that goes with millimeters of mercury. Or you're going to have to convert millimeters of mercury into atmospheric pressure if you're going to use the R value for atmospheric. The millimeter of mercury value from the table in your book is going to be 62.4. And then all the units that follow. I'm not going to mess with those units right now. Because I want to keep this brief. So that's the number I'm going to use for that. This one's fine, doesn't need to be converted. This one needs to be converted. We need to find this, and you need to finish your conversion over here. So this grams is going to go here. And this one's from the periodic table. So you're still going to have to do some math here. Okay? Hopefully that helps you out a little bit. At least gets you set up. But the balancing, you should always do that close to the beginning. I just happened to see that I need to do a quick conversion here, this one. So I went ahead and went for it so that I could have all my correct units in here. This needs to be in moles. And that way I have fill in all the blanks, and then you just plug and chug through here.